Metabolic adaptation to fasting occurs in distinct chronological stages, each characterized by specific hormonal shifts and fuel preferences. In the first 4 hours, the body is in the absorptive state. Exogenous glucose is the primary fuel, and high insulin levels promote energy storage. From 4 to 16 hours, we enter the post absorptive phase. Liver glycogenolysis maintains blood glucose as insulin falls and glucagon begins to rise. By 16 to 24 hours, glycogen stores are nearly depleted. Gluconeogenesis becomes the dominant process for glucose production. Between 24 and 48 hours, the liver ramps up ketogenesis. Fatty acids from adipose tissue are converted into ketones to fuel the brain and heart. Beyond 48 hours, the body enters a starvation state. Ketone reliance peaks, providing a protein sparing effect to preserve muscle mass. To understand how these stages are controlled, we must look at the specific enzymes and signaling pathways involved. Glycogenolysis is initiated by glycogen phosphorylase. Once depleted, the liver uses enzymes like PEP to bypass the irreversible steps of glycolysis. Regulatory enzymes like fructose 1,6 bisphosphatase and glucose 6 phosphatase allow the liver to export free glucose into the bloodstream. Insulin signals through a tyrosine kinase receptor, activating a cascade from IRS1 and PI3K to AKT, the master regulator of glucose uptake. AKT signaling induces GLUT4 translocation to the cell membrane, facilitating glucose entry into muscle and adipose tissue. During fasting, low insulin sequesters GLUT4 inside the cell, ensuring that glucose is prioritized for the brain via GLUT1 and GLUT3. This environment also activates hormone sensitive lipase, flooding the liver with fatty acids for ketone production. Prolonged fasting leads to total body electrolyte depletion through osmotic diuresis, creating a high risk state for refeeding. The insulin spike following refeeding activates the sodium potassium ATPase pump, driving potassium into cells. Simultaneously, the rapid resumption of glycolysis requires large amounts of phosphate and magnesium as cofactors, pulling them from the serum into the intracellular space. This mass migration causes a profound drop in serum concentrations, leading to clinical hypophosphatemia, hypokalemia, and hypomagnesemia. Monitoring and slow nutritional reintroduction are critical to preventing these dangerous electrolyte shifts.